So the Wednesday when we get back, we're going to try a remote day where students do not come to school that day. And I have to look at my schedule. About a week and a half ago, they gave a schedule, and they said, you guys have to do Zoom, and you guys don't do Zoom. Nobody wants to see 6 Zoom. You don't want to be at home and watch, no. So they picked, and what we would do is, if we were to go remote, and I keep praying about that. I think we're doing well. If we did go remote, it would be the same schedule every day. 1, 2, 3, 4, 5, 6, like that. It'd be all the same. First period like this. And that's the schedule we're going to be on Wednesday. So Wednesday is 1, 2, 3, 4, 5, 6. Okay. Now, I will look again, but I believe more of the humanities teachers are doing more live. I think they were doing most of the Zoom meetings. Did they tell you about that yet? Okay, they gave it to us over a week and a half ago, so I got to go look again. And but that's going to be the Wednesday after we get back. I don't believe I'm Zoom. I believe so I have a choice. I can actually pre-record a lesson, and you could watch that. It might be a 30-minute lesson, or I could just have you do something. It'll be on Google Classroom, take notes or something. I could do something like that. So, but I won't be doing a Zoom day on that day. We do have the week we get back, and then I'm not sure if we have 2 or 3 days. I got to look at that again. The exam schedule. The exams are starting earlier. And so it's not really the end of the quarter. It's just you want to have exams before you leave for Christmas. And so what I have to do is I know we're going to do one more chapter. I know we're doing one more chapter, but I don't see how I could do 2 in that amount of time. So so you would have a test on this, not next week, but probably the Monday after that. And then the exams would be the end of that week. Now, have they posted the exam schedules yet? I don't think, I'm pretty sure science is not on the first day. I don't think any science exam is on the first day, but I need to catch up myself. I need to start printing some of this stuff out, and because it's actually getting closer and everything. So when you have your exam, most of your exams are going to be shortened. Like I would have had another chapter on that exam, but we don't have time for that. So I'm going to have to make a decision on that. When we get back, we have not quite 2 weeks, but a week and a half. And so we're going to see how that goes. I just don't see how I can get chapter 19 and 20 done in a week and a half. I don't want to do that. So I'm going to have to modify some things myself. So. Okay. What do you think? Everybody? A little bit of announcements. The big thing is have a nice vacation. I want you to have a nice vacation. And hopefully you still get to see your family. Maybe you won't have as big of a gathering. I don't know how big your gatherings are. Ours will be smaller this year. We have some relatives that we used to get there in South Carolina. We probably won't be meeting with them. They've been very isolated. He has a little bit of health concerns. So anyway, we have to do things a little differently this year. And okay, so anyway, so Wednesday when you get back, that's going to be, you don't come to school. And then the week after that, I'll look on the exam schedule. You probably start then. Also next week, by the end of the week, I'm going to have everybody have a file folder, and we'll have your old tests. We'll stick them in there, and if you want to take them home that weekend, you can. But like I said, I don't think my exam is first day. I'm pretty sure it's not. So you would have time to study for that if you want to. All right. All right. Well, let's get started. And we have one good day today, and what we can do in this new chapter, chapter 19, is, and by the way, you do have a homework assignment, just like before. I need to grade your other one, but it does include drawing some drawings and answering some questions and taking notes. I'm not giving you homework for Thanksgiving, but if you could do some of that, you could do some of that tonight. Then you could say, I've done a little bit. At least I've started the chapter. And then you could just forget about it over the vacation and just wait till you get back. You still would have over a week. You'd have almost a week when you get back before the homework would be due. All right, here we go. Anyway, what I'm going to do is, the chapter we just got done was the physics of solids. And this one, I think is I thought that was very interesting. We talked about remember scaling, and we talked about arches and cantilevers and that kind of thing, and we even talked about density, specific gravity. That was kind of interesting. I liked it. I actually like this chapter even better. This chapter is on liquids, and it also will get into pressure. If you remember the big six, we had? The one I didn't spend very much time on yet was pressure, and that's because we have this chapter has pressure in it, the next chapter has pressure in it, so I knew we were gonna get that. So I think you're going to enjoy this chapter. I hope you will. It answers some questions that you may not have ever asked before. Like, for example, if things are more dense than water, what do? They sink. And so steel, which is mainly iron, has a density of about 8 grams per cubic centimeter. So what's going to happen with steel and water? Okay, so what do we build the biggest ships in the world out of? Steel. And I will tell you that humans had a lot of trouble with this until really almost the 1800s, the mid-1800s. Before that, they would laugh at you if you think you could make a boat out of something that didn't already float to begin with. So if you thought you could make a boat out of stone or steel, they would laugh at you. And yet the principle by which it works was discovered in around 300 BC. So what happened here? What happened to humans if we knew a long, long time ago about this principle, but they couldn't even make a boat unless you made out of wood? I went to Purdue University, and I'm sure NC State has something like that because they're very similar in their science and engineering. And every year the engineering students had a concrete canoe race. You had to make a canoe out of concrete, and they had to go down this river and had a race. So it had to withstand some rapids and things like that too. But just to think, you can't make a canoe out of concrete. Well, they've been doing it for 50 years just at that one university. So we have some things to think about. We have, remember I talked about the big six again. You really have to know the difference between all those words. Let's take a look at this first picture. They have a fish in an aquarium, a little tiny bowl of water. And have you ever thought about that? Why do fish seem to be able to sit there in the water? Why don't they go up, or why don't they go down? Or they can swim up and down, but they can just sit there, can't they? How do they do that? Can you do that? Can you just go underwater and sit there? Well, if you're a scuba diver, the answer is yes. If you know about scuba diving, you know that you can have a BC compensator, a BC vest, a buoyancy compensator vest. Does anybody here scuba dive? Oh, you did. Have you done that? Have you worn a BC? Is that what they call a BC vest? Okay. Could you go underwater 20 feet and stay right there? Ah, excellent. There's a lot of physics in scuba diving. Did they make you take a class, or they just have a... Yeah, excellent. Hey, I'm impressed. I was 17 when I was certified scuba, but I lived in Indiana. Well, guess where we had to do all of our stuff? In the pool. Did you do it in a swimming pool? Okay, we did it in a pool. And in Indiana, then we had to do open water dive for our finals. We had to go, and guess where do you go in Indiana to make a dive? Well, some places are lakes. There are lakes. You could do that. But we had to go to a rock quarry. You know what a rock quarry is? They dig out rocks, and there's a big hole, and then fills with water. And it was probably 100 feet deep. The rock quarry had 100 feet of water in it. And one thing about Indiana for sure is even if it's warm outside, you go down around 10 feet, and you hit this really, really cold water underneath it. And it's shocking. You probably didn't do that, did you? No. Okay. How far down did you dive?
60 feet.
Wow. Impressive. And when did you do this? Just last year?
Year and a half ago.
Wow, I'm impressed. Anyway, there's a great deal of physics in scuba diving. We'll talk about that. And so I think you'll enjoy this chapter because there's a lot out in the world that's based on this stuff. I understand that if you'll just give me your attention today, I understand that you're kind of going to check out tomorrow and you'll be on vacation. You get that? But let's not check out today. How about that? Let's get a good start today. All right. First of all, I want to mention to you that we're starting, if you were in physics, if you were in college, of course, they would use calculus. I'm not using calculus, but they would call it fluid dynamics. So this is the first of the 2 chapters that has to do with fluid dynamics. Now, what is a fluid? What's interesting, a fluid, you say, I think liquids are fluids. They are, but so are gases. And gases, anything that flows gets under the aspect of fluid dynamics. So we're going to do that. Now, we're not, if you went to college in engineering, you did fluid dynamics, that would be a very difficult class. They would start using all kind of calculus and talk about fluids going through pipes and stuff like that. That'd be a very sophisticated class, all right? All right, let me go over here now. And let's take a look at this picture here, all right? Everybody with me on page 363. All right, well, first of all, you already know what I want you to know. We did the last chapter, and here's your pressure equation. P equals force per area. Pressure is not force, it's force per area, so it's a ratio, isn't it? We have to be a little more careful with that. But the other thing I know we can do is we can take it out. What if I take that equation out? And I don't have to take it out of the fraction for you guys to understand it. You're very smart. But, I mean, I could do it that way. I could say, P and F are directly proportional, P and A are inversely proportional. I could leave it that way. But if you see it in like this, here's what we taught last chapter. P and F are, help me out, P and F are, they're on opposite sides, the equal sign. What? P and F are directly proportional as long as what? As long as area is constant. And I talked about that a few before. What if I have a knife that's not very sharp and then I sharpen it? All right. So what happens? I'm sorry, that's wrong one. If I were to double the amount of force I put on something, like I press on a cube, I double the amount of force, then I'm going to double the amount of pressure because the area stayed the same. All right. How do you know? What about A and F? How are they related? No, they're also on opposite side of the equal sign, aren't they? So how are A and F related? Directly proportional as long as P is held constant. So if I had a constant pressure, and I made the area get, if I made the force get 3 times bigger, what would happen? The force is 3 times bigger, but I don't want the pressure to change. What would I have to do? What would I have to do with area? I'd have to make, no, they're directly proportional. So if I want the pressure not to change, but I know the force is increasing, then I have to do what to the area? If I make the force 3 times bigger, I have to make the area 3 times bigger, or else the pressure will not stay the same. Now, if you can already do that, oh, one more. And these are on the same side of the equation, right? So they're inversely proportional. If you hold force constant and area goes down, then pressure goes up. We did talk about with a sharpened knife. Here I put a certain amount of force on a knife blade, I can produce a certain amount of pressure. If I sharpen the knife blade and the same amount of force, okay, the area now gets smaller and the pressure will get what? If the area gets down to, let's say, 1/10 of what it used to be, then the pressure will go up by how much? 10 times higher, right? And so that's why sharpening a knife works, because with the same amount of force, you seem to be able to cut easier because you're producing more pressure. They even have cutters that are called pressure cutters. They actually use high pressure water, or you can use high pressure water with sand in it, and actually can cut things with a pressure cutter, because that's really what's cutting anyway, pressure. All right, what do you think? You okay on this? Let's go down. All right. Excuse me. The one thing, this picture here, you say, well, why even draw that picture? Why even draw that picture? What if you had a block of steel here? Yes.
I just want to know more about it.
Yeah, sure. what if you have a block of steel here? Would you think that that block of steel was exerting a pressure on that piece of wood there? You say, well, yeah, I think so. And how much pressure would it be? How would I find the pressure on that piece of wood? I know it's Monday morning. Let's see if we can crank it up a little bit here. Yes.
Well, you would find the weight of the and then convert that to
Excellent.
newtons.
We might know the mass, but I need the weight, don't I? The weight is a force, so I need the force. I need to measure the area. And does anybody happen to know what units are used in the SI system for pressure? Pascal. Do you know what a Pascal is, though? Okay, Pascal. If you have 1 Newton of force over a square meter, that's pretty big. A square meter is pretty big, right? And a Newton of force is pretty small. So Pascal is not, it's a pretty small amount of pressure. Some of the good science fiction shows, when they say the pressure is building up, they actually do use kilopascals. Have you heard that anywhere? If you hear about kilopascals, it takes that's thousands of pascals, isn't it? So anyway, they're still using that. All right, now what I'm going to show you is, what about this right here then? Why show this picture of liquid next to a piece of steel? I know the piece of steel is exerting a pressure on that, but what about this water? Do you think this a jar of water is also exerting a pressure on that wood? Okay, what do you think? Now, what if this liquid was mercury? What if the liquid is not water? What if it was mercury, same volume? Do you think it might exert more pressure? What do you think?
Yes.
So, does density play a role in this? If this liquid is more dense, it weighs more, doesn't it? And it's going to have more weight per area. And so when they have this little statement here, it says the pressure of a liquid at rest depends only on gravity and the density and the depth of the liquid. Now, I'm going to show you something here. Not there. What they're trying to say is, if we're dealing with just water, though, let's say we're doing all of our experiments with the water, then the density is not going to change, right? If we do all of our experiments on the Earth, then the gravity is not going to change. Is that right? So then, what is the only factor that might determine pressure in liquids? If we assume that all of our experiments are done in water and all our experiments are done on the Earth, then of those 3 factors, the only one that really matters is what? No, if we're all doing all water, then the density doesn't change. One more. What is it? Depth. So let's take a look right here. This picture down here. Why are they drawing this? Because if I had a block of steel here, for example, and it had a certain weight area and it had a certain pressure, what do you think would happen if I put 2 blocks of steel together? Now, there's 2 ways of doing that. You can think about it this way, or you can also think about it through the equation. What I did is the area stayed the same, and I now have twice the force. If twice got 2 times bigger, what's going to happen to pressure? What do you think? Maggie, tell me, you know. If I didn't change the area, so area stayed the same, but I now have 2 blocks, 2 times the force, what's going to happen to the pressure? Say it again?
2 times the pressure.
Right. So if the force gets 2 times greater, very good. The pressure gets 2 times greater, right? See, the reason they did this, it says, that's kind of obvious, isn't it? If that was underneath your head, I had 1 block of steel underneath your head, then I put 2 blocks, you say, yeah, something's going on here. I'm feeling more pressure. You are. And then look what they did. They filled this with this much water, and then they filled it with twice as much water. What's the author trying to get you to say? What is the one factor that's going to make pressure greater here? Depth. We're not going to leave the Earth, so Earth's gravitational constant will not change. We're not changing the density of this liquid, so this depth only. All right, let's go over here now. So you see this equation. It says pressure due to liquid has to do with density times little g times depth. So it looks like there are three factors involved, but one more time, if we don't leave the Earth, we're not going to the moon, then this is going to stay constant, so we don't have to worry about it. If we don't change the liquid, then we don't have to change about that, and then it's strictly depth. Now, I certainly in this chapter, though, am going to talk about this, because we have ships that float, and sometimes, we have ships that go from the Great Lakes, and they actually can now go into the ocean. Anybody know, what do they do? How do they get ships to go from the Great Lakes? By the way, it's actually uphill. How do you go from the Great Lakes to the ocean? What do they call those things where the ships, a ship goes in, and then you fill water up, and the ship, it's like little stair steps. Ooh, there's no way you wouldn't have this. Anybody know? Raise your hand if you think you know. Yes, yes. Are you from Michigan? Okay. Have you ever been up there then? Okay. So you've seen them, haven't you? You've seen them work, haven't you? They're called locks. Have you heard them? Well, anyway, there are ships then that can go from freshwater to saltwater. And what's going to happen? What's going to happen to the amount of pressure that the saltwater can exert versus freshwater? Well, it weighs more, doesn't it? Not a huge amount more, but a little bit. Have you ever been in freshwater and you're kind of laying there and said, hey, I'm just sitting here and a little bit of my body is above the water. I'm floating on my back. Okay, let's go to the ocean. Float on your back again. Is the same amount of you underwater? What's going on there? What if I went to the Great Salt Lake and I float on my back? Would it have the same amount of me floating above the water? No. And the Dead Sea, probably the saltiest water on the planet, you'd be floating even higher. But what if I had you float on your back in a pool of mercury? What? How much of you would be underwater then? Almost none? I don't get that. And so we're gonna take all these things we're gonna explore, and I think you'll enjoy them. Let's go to the next one. Maybe you never thought about this, but how big of a dam do you need to build? If you want to build a dam, how big do you need? True or false? It has to do with the volume of the water in the lake. What do you think? That makes sense, doesn't it? If you have more water, you'd have to have a bigger dam, wouldn't you? That's not true. I could have a huge lake, huge, but what if the average depth was only like 30 feet? How big of a dam do I need? Not that big. Whoa, it's a huge amount of water. Water has pressure in every direction, right? But I don't want to worry about that. It's the depth of the water, isn't it? And when they build a dam, look at this. Why do you want to build a dam thicker at the bottom than at the top? Why? Why is there more pressure at the bottom than the top? Depth. What about a kind of a small lake, but it's 100 feet deep? How big a dam you need for that? A big one. Why do you need such a big dam for a small lake that's 100 feet deep? What's the word? Starts with a P. What's the word? Pressure. I need a huge dam for that. Here's something that's interesting here, and I know I'm moving at a good pace here, but which of these objects, here, 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 or here, I put little dots here, which of those objects do you think is experiencing the most pressure? Which one was experiencing the most pressure? David, what do you think? Give me a guess. I know we're just starting this chapter, so you're just guessing anyway. You think that object, this one, or that one, which one is experiencing the most pressure?
I think they're all experiencing the same amount
Why do you say that?
Because, well, they're all in water and they're all at the same depth, it looks like.
That's great insight. That's great insight. That's true. That's true. We might think, whoa, oh, look, there's more water here. And so this is going to have more pressure. And look at that water. Whoa, oh, okay. But you're right. It has to do with depth, doesn't it? And I think that's what they're trying to get you to think about here. Now, the good news, even though we need a gravitational field for weight, don't we? For force. So I do need a gravitational field, but what's interesting is, even though it's the weight of the object that's going to cause pressure, what happens when water pushes down? It also pushes this way and this way and this way. So water pressure is the same in every direction at that depth. Here's what they're trying to show here with this object. Which side of this triangle is experiencing water pressure? All of them, all the sides. Here's something I'll do when you get back. I'll do a demo when you get back. I have actually a 2-liter bottle, and I made some neat little holes in it. And what I'll do is I'll fill it, and it'll be full, and I'll have a hole here, and a hole here, and a hole here. And when I let go of it, what's going to happen to the water coming out this hole versus this one versus this one? And if you look right here, what is the amount of force that's pushing the water out this hole compared to the amount of force pushing out that hole? And I have all 3 holes are the same size. So I don't have a huge amount of force pushing on the water here, do I? And force per area is what's it called? What's force per area? Pressure. So I don't have a lot of force per area pushing water out, so it doesn't accelerate very much. But look down at the bottom. Woo! And I'll tell you something that's interesting. If you want to do something fun, sort of fun, you can make a cup. You can get a styrofoam cup and try to put 3 identical size holes in it, okay? And then put some tape on the holes, fill it up with water, okay? Now get on a ladder or a chair. If you don't fall. And what you do is you take the tape off, and you're going to see the bottom hole water will shoot out faster and go further, right? You say, hey, more pressure, less pressure, right? Then once you take the cup and drop it. Take the cup and drop it. Anybody know what's going to happen there?
Will they all come out at the same speed?
That's a good guess. Do you know why? Anybody know? All right, that's one guess. Anybody have another guess? If I do this on a styrofoam cup, all right, ready? I'm up on the chair, and I take the tape off, and they go, woo, 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 like that, and then I let go of it. What's going to happen? Yes?
They're going to stop flowing.
That's right. They'll stop coming out of any of the holes. And as objects in free fall. And we'll talk more about that during the year, but in free fall, it's almost as if it's, quote, weightless. It's, quote, weightless. And so we actually don't have some of those forces pushing on up and down and sideways like that. All right. Now, let's go over here. And I have a, let me see if I can find it. Uh-oh. Okay. I had a student last year who did I don't know where they found this, and I think it's kind of fun that people can still have fun with nerdy things. I always thought this word was spelled weird. Do you like how it's spelled? Buoyancy. Buoyancy. Okay. No? Is that too early on a Monday to do that? Okay. All right. Okay, hopefully. No, it's buoyancy. Well, anyway, we're gonna after we get into this stuff here. This is the good stuff. This is probably the best stuff that you can look at. And what I want to do is, how many of you think you understand buoyancy? Have you ever experienced buoyancy? Have you done that? Have you ever tried to lift somebody up out of the water and say, "Wow, you're pretty heavy," and you go in the water? Can you sometimes hold them up with one hand? And like I said, why would we want to build the biggest ships in the world out of something that's 8 times more dense than water? Why would we do that? And it's this word right here. Density tells part of the story. This tells the other part of the story. You get that? So the first question I'd like to have, when you draw this drawing, do you notice how the arrows down here are bigger than the arrows here? Why is that? Wow. Let's see. Kieran, help me out here, okay? Why would the arrows down here be bigger than the arrows here? Hang on just a minute.
Well, there's less pressure on the top because there's less spin.
And pressure is force per area, right? So if I look at a square centimeter here and here and here and here and here, the force per square centimeter is less here. Why is that? So why now?
Less pressure,
Why?
there's less depth.
Yes, that's exactly right. So the question is, why is it that a buoyant force always acts up? Why does a buoyant force always act up? If you take a look, take all these vectors here and add them to all these small vectors, and what do you get in the vector world? Up or down, side, what do you get? Up. So the net force, called the buoyant force, is always up because of depth. Even my hand, if I put my hand under water, there's still a little more pressure here, more force here than there is here, right? And I'll actually feel a buoyant force up there. So, a buoyant force is an upward force. As you push the water down, it pushes back. You end up having a net force up. Now, we're in this vector world still, and so what I'm going to show you something. Here's something you had last 2 chapters ago. A completely submerged object displaces a blank of water equal to the object's own blank. Do you know what goes in both those blanks? What do you think, Nathan? A completely submerged object displaces a blank of water equal to the object's own blank. That's in the first blank. What about the second? A completely submerged object displaces a volume of water, I agree, equal to the object's what? No? See this extra water up here? Where did it used to be? It used to be right there. And what is it? What aspect of the rock displaces water? Color? Shape? Starts with a V. What? Volume. A completely submerged object displaces a volume of water equal to the rock's volume itself, isn't it? That's called the principle of water displacement. Yes?
We can't see what you're doing. Can you move the book down a little bit?
Okay, I'm sorry. Thank you. My fault. And this is something we learned 2 chapters ago. A completely submerged object displaces a volume of water equal to the object's own volume. Now that one's called water displacement. But I want to show you this over here and tell you why that's different than buoyancy. Okay, so here we have a picture here. And take a look at this. They completely filled this beaker with water, and they're going to put this rock in there, and when the rock goes in there, it's going to displace water, and for some reason, they thought, I'm going to catch that water. Oh, I don't know why. I think I'll just catch it. What are you going to do with it? Oh, I don't know. Okay, so they catch the water. If they were to measure the volume of that water, what would it tell them? Becca, you know. If they took the volume of that water, what would that tell them about the rock? The volume of the rock. But then, if you look on the next page, they do something kind of weird. That's kind of weird. We're going to catch the water, and we're not going to find the volume of the water. We're going to find the weight of the water. What? What are you doing? Why would you do that? Ryan, what do you think? Why would they want to take the weight of that water? And I'm not sure if anybody in this room knows that, so you might as well take a guess. It's kind of weird, isn't it? Why do you want to weigh that water? What do you think?
Because that's how you get to figure out the buoyant force.
What? Okay, let's take a look here. And I'm going to read Archimedes' principle. What we did a while ago is called the principle of water displacement. That's not Archimedes' principle. Here's Archimedes' principle. It says, the buoyant force on an immersed object, that means you could be either a little bit in the water or completely underwater. You get that? You're displacing at least some water. Maybe your whole thing's underwater or part of it. It says here, the buoyant force, measured in newtons, of an immersed object is equal to the what? One more time. The buoyant force is equal to the what? The weight of the fluid displaces. What? What? Who did that? Archimedes. Archimedes did that. And so, let's say you're an engineer, and somebody says, I have this ship I want you to build. It's the neatest ship in the world. There's a problem, though. It weighs 500,000 newtons. Okay. So, as an engineer, what do you have to do? It's not that simple. How do you get a 500,000 newton ship made out of steel to float? What do you think?
Make it like this, so that it displaces a lot of water.
A lot? Like how much?
Like a lot.
How much?
I don't know.
I know.
Like the volume.
500,000 newtons of water. If you weigh 500,000 newtons, and there's a buoyant force on you of 500,000 newtons, what are you going to do? You're going to float.
You'd be neutrally buoyant.
When an object's floating, which one's greater? The weight of the ship or the buoyant force on the ship? What do you think?
Buoyant force.
How many people say buoyant force? Oh, okay. How many people say weight? All right, let's say everybody has to vote. Ready? Here's a ship floating on the water. Which one's greater, the weight of the ship or the buoyant force on the ship? Ready? Who says buoyant force? One more time. You have to vote. You have to vote. 1, 2, 3. Pull that whole row. Oh, yeah. How many people say weight? How many people says another answer? What do you think? It's equal. You're right. Very, very good. Very, very good. You see, if buoyant force were greater, the ship would have to be going up. If weight was greater than buoyant force in the vector world, the ship would be sinking. Now, I agree with you. When they first put the ship in there, when they first put the ship in the water, weight was greater than buoyant force. And that's why it went down. And it went down. And it went down. And more of the ship went underwater. And then the ship stopped going down. Why did the ship stop going down? Boing. It had displaced enough water to equal the weight of the ship. This is something they knew a long, long time ago, and yet they couldn't figure out that you could make a boat out of something besides wood until maybe the mid-1800s. That was pretty neat. Anyway, Archimedes' principle, one more time. An immersed object, an immersed object is buoyed up by a blank equal to the blank of the water displaced. Let's try it. An immersed object is buoyed up by a blank What goes in there? What? An immersed object is buoyed up by a, what do you think? Force, called a buoyant force, equal to the blank of the water displaced. Weight. Wow. This is some good stuff there. All right. All right. Now, one more thing, and keep moving a little bit. Take a look at this drawing right here. This is one you have to draw for your homework. And look at the arrows. Well, first of all, there is pressure on that box going this way, and there is pressure going that way, but what is this amount of force and this amount, that much force going left, that much force going right? What's the net force in this direction? 0. What is the net force in this direction? Yes?
What happens if the object isn't perfectly symmetrical?
Okay, it doesn't have to be. That's a good question. That's a great question. Icebergs are probably like this. And then underneath the water, it's like, oh, okay. So this might be an iceberg. They're not symmetrical at all. So, hey, what's the net force in a vertical direction? What do you think? McKinley, you know. Is there going to be a net force in a vertical direction? Huh? Yes. You know why? That's called a buoyant force. And McKinley, one more. What is the net force of, what if I said there's this much force on the top of the block, but twice as much force on the bottom? Why? Why would there be twice as much force on the bottom than the top? And the answer starts with a D. Yes. Depth. Very, very good. This side here is always deeper than that side, so the net force is like that. Now here's what this drawing is about. Hey, you already taught me that. But now let's go down deeper. Let's go down deeper. All right, Ian, look at me. We're going to go down deeper, Ian. True or false? As you go down deeper, the pressure on the top of the block increases. True or false? The pressure on the bottom increases. Okay. The net force, the buoyant force, also increases. What do you think? Why is that?
Because it's directly proportional. It increases on top and also increases on bottom.
Wait, say it again.
It increases on top and also increases on bottom, so they stay the same.
Okay, so here, if we say that there's 1 unit of force here and 2 down, then the net force is 1 up. As we go down, now there's 3 units of force here, but 4 down here, so the net is how much? 1 up. If we get down really deep, there might be 5 units of force on the top and 6 on the bottom. And so what's interesting is the buoyant force actually stays the same. It's up, but it doesn't get greater as you go down. Yeah, the pressure gets greater. Great. It can get really great. But the net force is about the same. All right, so what we have in this chapter, and we're almost, it's hard to believe that if you understand the big 6 like you do, the learning curve was slow for a while. Now it's getting to the point where you can learn things at a faster rate because you're putting things together. And I'm going to show you one more thing here, and this is going to be the hardest thing for you, and I'm going to leave you with this. Why, though, if I take a block of steel and I put it like this, and I put it underneath the water, will there be a buoyant force on that block of steel? And will it be up? Will there be an upward buoyant force on that block of steel if I put it underwater? Don't let go of it yet. Is there a buoyant force in that block of steel? Yes, because it is displacing this much water. And that's how much buoyant force I get. Take the same piece of steel and shape it like this. Which one weighs more, this ship or that ship? They weigh the same. Now, this steel is displacing the same amount of water here, but what used to be here? What used to be on the inside of that ship? Water. Where is it? Where is it? Wait, where is it?
The ship.
It's been displaced. Okay, it's been displaced. So what's interesting is this piece of steel, and let me tell you something, this will be the last thing I'm gonna do today. There are two things, you gotta fight this with your brain. Archimedes' principle is true. This thing is being buoyed up. This thing is being buoyed up. But you gotta fight this because there's another issue, it's called the principle of flotation. What if the object's weight is greater than buoyant force? And you let go of it, what happens? It sinks. What if the weight is equal to the buoyant force? Then it floats. Whether it floats on top of water, it can even float 20 feet down. And what would happen if buoyant force was greater than weight? It would go up. And luckily, submarine captains know that when they're at the bottom of the ocean and they want to go up, they actually can have buoyant force be greater than weight. Okay, thank you very much. What I'd like to do is, I would start this as far as your homework. If you can do it, some of it tonight, then just forget about it over the Thanksgiving break. How about that? Do a little bit tonight and say, I got to at least start on that, and I'm going to put my book up and I'm going to forget about physics till I get back next Monday. Okay?